The extended Kalman filter. You want me to demonstrate the C++ or Java version? C++ it is, okay. Okay, save link as like temp Kalman CPP, okay. Unzip Kalman CPP.zip. There we go, I unzipped it. Kalman CPP, C source. I run my build script. Then it's going to build this darn thing. That is a darn good question. I have absolutely no idea. It's more than 2. And it's definitely less than 100 trillion, because that's the number of neurons in our brain. Unless, of course, there's some kind of compounding effect where each neuron encodes more than one value, one binary value, in which case, who knows. Okay, so you run the program, and then it yells at you and says, hey, you forgot these 2 parameters. I'm going to run it again and pass in 0, 0. And here we go. I made a crane simulator. Now, if I press my arrow keys, it moves around. And you see this grid? That represents the state. And the thing at the top, there's a picture of a crane. And I can drive around my state, and you can see the crane kind of mirrors with a little picture. You can even go out of the state and see what irrational things look like if you want to. And it figures out how to generalize pretty well in that direction. Here it just disappears. Ooh, let's see what up does. Just goes up. Well, up and down generalize pretty well. But this is a 2-dimensional state space. So in the ideal value for Z, the ideal number of elements for Z here, or the true dimensionality of the state space, is 2. And we know that because there are exactly 2 degrees of freedom, and there's nothing else in this problem. And you'll never really encounter a real-world problem this simple, but that's okay because it's just a demonstration or a proof of concept. I also like 2-dimensional things because you can plot them on a grid and people can wrap their heads around it. And it's good to start with something like this before you move on to a real robot. Okay. The picture here is a 64 by 48 pixel image. There's 3 color channels in it. So if we do the math, that is a 64 times 48 times 3, 9,216 dimensional vector to represent that image. I'm not sure why there's this white band bouncing up and down here. I swear that wasn't there yesterday. That probably means there's an uninitialized vector somewhere in my code. If you happen to find bad programming, I apologize. Please call it to my attention. But yeah, anyway, that's what we have to work with. So here's what you're going to do. You're going to apply the Kalman filter to this thing. Oh wait, I got to show you what the parameters do. Let's suppose we pass in 0.1. Now what we see is the picture is a little bit noisier. See that? I don't know if you can see it very well. Okay, well, let's crank it up to 0.9. Now you can see it's noisy, right? Basically what I've done is I've added Gaussian noise to every pixel as you're watching that image. Okay, can you still see where the crane is through the noise? That's because you're intelligent. Okay, let's crank it up to 10. Now try and see the crane. At some point, I'm going to overwhelm you. If somebody could actually see that, I'm going to crank it up to 100. But the point is, there is a point at which no human, no level of intelligence could possibly discern what is going on there. Okay. The other parameter we have to mess with is the first one. Let's do 0.1 comma 0. This one is transition noise. So if I press to the left, notice where the dot went. Not going very straight to the left, is it? Now if I point to the right, it's going like this. There's a lot of transition noise there. Okay, so 0.1 is pretty bad. Let's go 0.02. That's a little better. See, now it's jittery, but not horrible. And if we were to crank that up all the way to 1 or something like that, it would be utterly uncontrollable because I'll just push to the left and jumps way over there, right? I push to the right and it goes who knows where into irrational space. So you could obviously kill this thing with noise. Your task, should you choose to accept, and you will, or face grade penalties, is to try to estimate where the state is. Now, obviously, you could just look at the state and it's right there. But you're going to put a dot on here where you think the state is while deliberately refraining from looking at what the state is. So basically, you're going to look at the noisy image, you're going to know what the image says, and you're going to know what actions you've performed, what your keyboards have pressed, and you're going to see what pixels are coming in, right? And based on that, you're going to calculate where the state is, and it won't actually be a point, it will be a Gaussian, well, it'll be a circle. And the less you know, the bigger the circle will be. And the more you know, the smaller the circle will be. So the Kalman filter is actually a provably optimal way to estimate state given some assumptions. Those assumptions are the noise must be Gaussian. Turns out in this case they are. And there's good reasons to assume noise in general is Gaussian. Maybe we'll talk about that when I have more time. The transition models and observation functions that you have also need to be accurate. In this case, I'm giving you those models. So I have trained two neural networks. One does the transitions and one does the observations. So you're given the models and now you're just going to work with it using the Kalman filter, if that makes sense. So you don't have to actually worry about training the neural nets. I have another class where we actually do that with this very problem, in fact. So hopefully my problems will fit together to help you form a cohesive understanding of the universe at some point. This one doesn't do convolutional neural nets. It actually does kind of reverse convolution. Here's the way it works. I take the state and you also pass to it the pixel of interest, the x and y position of the pixel you're looking at, and it applies a model to predict that one pixel. So if you were to sweep across the whole image, it would essentially apply the same model to every part of the image and thus predict the whole image. You see how that's kind of backwards of convolutional neural nets? Yeah. So the more we dig in, you'll see what I'm talking about. And we'll talk more about this next time. I'm a little out of time. But suffice it to say, you'll know the actions you performed, and you'll have the images, and your job is to put a crosshairs on here where the dots, where the state is. And then we'll fiddle with the noise and see how much noise your Kalman filter can handle and still compute where the dot is. Okay. Thanks for coming. See you next time.